Okay, so today we're looking at the topic of volume, and we're going to look at a very specific type of volume questions in this section, and these are the volumes that are obtained by solids of revolution. So these are going to be perfectly symmetrical figures, and the cross sections are always going to be circular. Okay, so we're going to look at volumes of solids of revolution. Now, up to this section, like in geometry, without using calculus, we know how to find certain volumes. For example, volume of a sphere, volume of a cone. There are certain well-known figures, like volume of a pyramid from geometry, a cylinder. But what do you do if the region that you have is something like, let's say you take this region that is given by y equals f of x, and you rotate that region around the x-axis, let's say. So you end up with something that is not necessarily a known figure. So how do you find the volume of a figure that is not a well-known geometrical solid? There's no specific formula for it. That's where the calculus is going to be helpful to understand how to find volumes of such situations. Okay, just another thing I want to point out once again. Here we're doing volume of a solid of revolution. In Calc 3, you're going to be able to do volumes of not just solids of revolution, but basically any function bordering the top and another function bordering the bottom. It doesn't have to be this perfectly circular shape, okay? But in this class, we're looking at a very specific case, which is a circular cross-section type of figures. Now, to be able to explain the answer, to be able to get the formula for that, we have to start with something very simple, which is the volume of basically a solid of revolution, but your revolution just consists of a rectangle. So consider this first picture that I have here, the first rectangle, this one right here. And here you have a rectangle. What we're going to do is we're going to take this rectangle and rotate it around the axis of revolution, in this case the x-axis. Now what kind of a figure do you think you would get when you do that? If you rotate that, a single rectangle around the x-axis, you get a disk basically, which we see the picture roughly on the right-hand side. That's the disk obtained from that revolving that rectangle. And notice the rectangle is bordering the x-axis. There is no hole there because we're going to look at the regions with a hole in just a little bit. And basically you have a rectangle, a thin rectangle, that is perpendicular to the axis of rotation. Okay, so when you have this and you go around the axis of rotation, you end up with a disk. So before we can understand the volume of a solid of revolution, let's first remember what we know about the volume of this disk. And in your handout, you have some spaces that we're going to be filling in. So suppose the rectangle's dimensions are W by R. So what would be the volume of this disk then? In general, what is the volume of a disk? If it's a circular cross-section, right, pi r squared, which is the area of a circle, times the thickness, right? In this case, your r is given by the capital R, and what is the thickness? W. So what would be the volume of this disk that we generated? Basically, pi r squared times W, right? So that there we have it. The volume of one disk is pi r squared times W. If basically the height of that rectangle was R and the thickness was W, that gives you a disk with a radius of R and thickness W, and the volume of that is pi r squared times W. Okay, now we're going to try to answer the original question that we have. So the original question that we have is the following. We don't want to rotate just one rectangle, but we want to rotate an entire region, such as the one that is over here that is shaded by the blue color. So you take that region and you rotate that around the x-axis. What will be the resulting figure? That is what we call a solid of revolution. So if you take that region bounded by the black curve there, call it y equals r of x, you rotate that around the x-axis, and you end up with basically the solid that we see in the middle picture here. But in order to understand how to find the volume of that, we're going to split that region into n rectangles. So if you take just one rectangle, see what's happening here? If you just take one rectangle from that region, and you go around the x-axis, you get one of these disks that you see on the right-hand side. So you take two rectangles and you have two disks. Let's say we take n rectangles, so we're going to have n disks covering the region. Now to find the perfect volume, guess what we need to do? Guess how many disks we're going to need? infinitely many, just like the area under a curve, you needed infinitely many rectangles. Here you're going to need infinitely many disks. So if we know how to find the volume of one disk, and we add n of those, and we take a limit as n goes to infinity, we're going to have the formula for the total volume of the solid of revolution. So that's what we intend to do. So let's start by writing the volume of this one disk that was generated by this thin rectangle. It's very similar to the rectangle we had above, but the thickness is not double D, it's delta x right now. So what is the volume if you take this? If you take this rectangle here and if you rotate it, you get something like this, right? One of these disks. So the question is, what is the volume of each one of those disks? We represent it by the notation delta W. Okay, delta W represents the volume of one representative disk. Okay, it's an incremental volume amount, the volume of one disk. What is the volume of one disk? If it's generated by this rectangle that we see here in yellow, or so what is the volume going to be? So instead of W, what do we have? Delta x. So it's going to be pi times. Now, it depends on where your rectangle is, right, as to what the radius is going to be or what the height of the rectangle will be. But at the moment, let us assume that this function is given by, let us assume that this function is y equals r of x. So it's not a constant function. Depending on where you are, the height is different. So now what is the volume of that one disk that is generated by rotating this rectangle around the x-axis? It's going to be pi times r of x squared, right? Pi r squared, but r is not a constant depending on where you are, times the thickness, which is delta x in this case. Instead of W, we have delta x. So that's how we should fill in the next blank. That means the volume of one incremental disk, which we call delta W, is pi r squared times delta x. Okay, that was just for one, right? But what do we really want? We want the total volume. So let's take n of those rectangles. We're going to take n of them to cover the region in the beginning. So what do you need to do with these n disks that you have generated? Pardon me? First, you want to add them up, right? Because you have n disks, so you want to add up the volume of the first disk, the second disk, all the way to the last one. So go ahead and sum this up, because we want the summation of delta W's or delta V's. We want the sum of these incremental volumes. That will be approximate answer, the summation as I goes from 1 to n. Basically, we're taking the answer from the previous step, but I just added a subscript of I because I want to represent there is one rectangle, the second one, the third one, all the way to the nth one. And you see I have a summation in front. Summation represents I'm adding these n solids. So I have a summation of the previous answer, which gives you the sum of n disks. Now you see the wiggly signs. This is a rough answer. It's not the exact answer for the volume of the solid. How can we find the exact volume? The exact volume should be, we take the answer from above. So I'm putting equal sign here because this is going to be the exact volume, not approximate. So what should I do to the expression from above? Take a limit as n goes to infinity, because you want to add up now infinitely many of these disks. Okay, so take a limit as n goes to infinity of the answer from above. And you could pull the pi out if you wanted to. That's just a constant. And what have we learned? We reviewed this last class also. What is the shortcut notation for limit of a sum of this nature as n goes to infinity? What was the shortcut notation that we used for that in calculus? The integration symbol, right? The elongated s is really representing an infinite sum, basically, right? So that's what we have here. We have, if we now rewrite this with the calculus notation, we will put an integral sign, replacing the limit of a sum. You would need an integral sign. The pi z constant can be taken outside. Inside the integral sign, I'm going to have, in simple notation, r of x squared. And what does the delta x usually become in your integral notation? Dx, right? And do we have limits of integration on the x-axis? Yeah, it looks like it was from x equals a to b. So I'm going to put the limits of integration as a to b. So the volume of the solid is going to be given by this formula, pi times whatever the function was. If the function is y equals r of x, then you're squaring that function dx, and then you're integrating it. That will give you the total volume of that solid of revolution. So just to review what we just have seen, put up a little bit. So we begin, you know, this is like a common theme in every section that we're covering in this chapter. Like when we did area, first we picked a representative rectangle, and what was the area of the rectangle? F of x minus g of x times delta x, right? Then we integrated to find the total area. Here, our representative formula, our representative disk had a volume of pi r squared w. From there, we went to basically, instead of w, we use delta x for our problems if the thickness is delta x. And again, when you sum it up and take the limit as n goes to infinity, you end up with pretty much the same expression, except you have an integral sign in front and the limits of integration a to b. Just remember, integration is basically doing an infinite summation for us, finding that total area. So just to give you a general idea here, in this section, the way we're finding volume, think of a big watermelon or a cucumber or something and slice it down, okay? So basically, each of the slices is a disk, right? So if you add up these slices, you have the total volume, and each slice is basically going to have a different radius, but that doesn't really matter because integration is taking care of that for us as long as you know the equation of the function that borders the region. Now, sometimes we're going to select a rectangle that is perpendicular to the y-axis. In this example, we saw that the rectangle was selected perpendicular to the x-axis, like the one on the left over here, right? When that went over the x-axis, you ended up with your figure. But sometimes it'll be more advantageous to select a rectangle that is perpendicular to the y-axis. Or a question might say, rotate this region around the y-axis instead of the x-axis. If that is the case, we must begin by selecting a rectangle that is perpendicular to the y-axis. So your formula will be very similar, but instead of, if you look down here, instead of r of x squared dx, you're going to have r of y squared dy, and one could again do a very similar approach. Start with one rectangle, select n rectangles, take a limit as n goes to infinity, and you're going to end up with this formula. So depending on the question, whether or not the rotations are on the x-axis or the y-axis, we have to set the problem differently. And basically, these are some tips that we're going to use in every example that we solve. First of all, with the disk method, the method we're learning today, that is, your representative rectangle should always be perpendicular to the axis of rotation. That is creating the disks, basically, okay? Now, contrast that with the next section, where we're going to learn something called the shell method. Now, for the shell method, think of an onion. Okay? You have one layer within another layer within another layer. That's the way we're going to build volume there, okay? So in that section, instead of dealing with perpendicular rectangles, we're going to deal with parallel rectangles to the axis of rotation. Okay? So in this section, when you are using the disk method, your representative rectangle should always be perpendicular to the axis of rotation, because that is what is creating the disks, basically. If you have a rectangle perpendicular and that goes around the axis, that is going to create a disk. So that is why you want your rectangle to be perpendicular to the axis of rotation. And once you know this, the thickness of the rectangle is delta x. That tells you everything, basically. It tells you all your variables should be in terms of the x variable, and limits of integration must come from the x-axis. On the other hand, if you're going around the y-axis, you're going to select a rectangle perpendicular to the y-axis. Here, the thickness is delta y. Again, that tells you everything over there. Your integral must be set in terms of the y variable, and limits of integration must come from the y-axis. This is really, really important. So for every question you're doing for your group activities, your homework, quiz, you name it, I'm going to require that you show me a picture, and on your graph you show me a representative rectangle that is properly marked with delta x or delta y. Again, by making this a requirement, hopefully I'm helping you to set up the problem correctly, because if you see that in front of it, a delta y, then there's less room for error. Everything has to be set up in terms of the y variable. Okay, now sometimes there will be a hole in the region generated. So the last few examples we looked at, the solid was completely solid, no holes at all, and to create a solid like that, your rectangles were bordering the axis of revolution. Now consider a rectangle like this one. It is not bordering the axis of revolution, and rotate that around the x-axis. We get the figure on the right-hand side. Now, what name could you give to that solid that is generated when you rotate that rectangle, not touching the x-axis? If you rotate it around the x-axis, what could you give? It's not a disk, right? What could you call it? Maybe a disk with a hole, or you could call it a washer, right? That's why this method is sometimes referred to as disk/washer method. If there's a hole in the region, basically you're looking at a union of a bunch of washers. So basically it's a disk with a hole in it. Now, in order to understand more complex figures, let's first understand this one single disk. In this case, disk with a hole, or really a washer. What would be the volume of this one washer? Any thoughts? Exactly. The volume of the bigger disk minus the volume of the hole, right? The volume of the inner disk, right? So what is the volume of the outer disk? So the volume of this washer equals volume of this one washer equals. Okay, so the volume of the outer disk. What is the volume of the outer disk? The outer disk has a radius of big R. So what is the volume of the outer disk? Pi times big R squared times the thickness, right, which is W, right? Minus, what is the volume of the inner disk? This time the little r, right? Lower r, okay. If you simplify that, what do you get? Factor out a pi times W, right? What do you get? Not just big R minus little r, but big R squared minus little r squared, correct? So if we factor out pi times W from both of those two terms, we're going to end up with what I have here on the right-hand side, which is pi times big R squared minus little r squared times W. So that gives you the volume of the washer. Yes, question?
On that example, if they put the W was put on, and sorry, if I put the W next to the pi.
Right, that doesn't matter at all because multiplication is commutative. Exactly. Okay, so we've done it for one washer. Now we want to do it for a number of washers and integrate it to get the total volume of the region. So say that we have a situation like this. We have this region shaded in blue, like you have on the left-hand side, that is going to be rotated around the x-axis. First, look what the resulting solid looks like. On the right-hand side, that's what it's going to look like. Like the inner part of the solid is a little bit curved, like the outside is straight. So basically, we're trying to find the volume of this region that has been generated. Does this solid have a hole in the middle? Absolutely. Anytime your starting region does not border the x-axis completely, then you're going to end up with a hole in the middle. So in that case, you have to use a slightly different formula than the one we worked with earlier. So we're going to begin by picking one representative rectangle from the region. So we pick one rectangle, such as this one. So we rotate that rectangle around the x-axis. That gives us one washer. Now, what is the volume of that one washer? So volume of one washer, which I'm going to call delta V, which is the volume of just a single washer. It's very similar to the last example, except instead of W, what is the thickness of this washer? What is the thickness here? It's delta X, right? Okay. So what is the volume of the washer obtained when you're rotating this figure around the x-axis? And by the way, the upper, because depending on where your rectangle is, you know, the upper point and the lower point are changing, right? But just know that the upper function is given by y equals capital R of x, and the lower function is given by y equals the small r of x. So with that understanding, how would you set up for the volume of one single washer? Pi times delta x times. Exactly. Now this is a function of x depending on where you are. So big R of x squared minus little r of x squared. That's just for one washer. Rotated, that take one rectangle, you get one washer. Now the volume of the region roughly will be equal to what? What should I be doing? This is just one washer. First, to get an approximation, I do n rectangles, right? So I do n washers. So what should I be doing to this? Sum it up. Sum this up as I goes from 1 to n. Again, I can take the pi outside. Delta x I will put at the very end. And inside here, I will introduce a subscript of x sub I. That tells me about when I use 1, I'm on the first washer. When I use 2, the second washer, etc. And I'm going to cut down some parentheses here, but I hope you still understand what this represents. So basically, the first quantity squared minus the second quantity squared. There. Okay. And finally, how do we get the exact volume? Take a limit of this as n goes to infinity, right? So exact volume equals limit as n goes to infinity of the above. Hopefully I can copy that myself. So again, pi is a constant. I can just take it outside of everything if I need to. Take the pi outside. And limit of a sum. So we're just taking a limit of same exact thing as you see above. As I goes from 1 to n. The first thing I pulled out was the pi. Right, 3.14. First capital R squared minus little r squared times delta x. And what replaces this limit of a sum in calculus once again? How can I use a shortcut notation for these two symbols? The integral notation, right? That's, again, the definition of an integral is exactly that. So if you do that, you get the formula for the washer method. So contrast this with the formula we learned a few moments ago. It was very similar, right? Take a look at that formula. We just didn't have the inner portion subtracted, right? We didn't have the minus little r squared. So when there's a hole in the region, there is something to subtract. But if this is, in a sense, your more general equation, because if there is no hole in the region, the middle part you're subtracting is 0. You're subtracting nothing. And if there is something to subtract, there's a hole in the region, then there's a place for that as well. But both of these techniques rely on the fact that you will select a rectangle perpendicular to the axis of rotation, look at whether that rectangle has the thickness of dx or dy, and set up your integral accordingly. And here I'm only giving you the example of the dx, but remember you can also set up the same integral in terms of the dy, where all the variables are in terms of y, and the limits of integration comes from the y-axis. At this point, I'd like to show you a few demonstrations that I found on the web, and then we're going to come back and do some examples. I recently went to a conference last semester. Actually, some of you were in my Calc 1 class, and I was in Washington. I met this person, Paul Seeberger, and he had this grant from NSF, and created some really great websites, especially for Calc 3 students. So if you're interested later on, I'm going to show you the website. Write it down, because if you take Calc 3, you may find that site very helpful. But here there are also a few examples about disc and washer method. So let's go to the washer method for now. It's amazing because he actually wrote these programs, the program that makes this run. So here you have a region, and you've selected one represented rectangle. So there are many things we can do with this. Let's play with it a little bit. For example, we can make it to show n washers. And how does it know what n is? Down here there's a setting. Like right now there are 4 rectangles selected from the region. We can increase this number. Like we can have more and more rectangles. Like right now I have 13 rectangles. Okay. Then I can revolve these rectangles. First it's revolving the represented rectangle. Again, it's perpendicular to the axis of rotation, so it's going around the axis of rotation. Now it's going to revolve all the rectangles. So there's our solid, and plus you can make it, you can hide the washers in the final step, and you can make it transparent, I think, to really see the volume that we've generated. So what we did was we started with a curve, a 2-dimensional area, right? We rotated that around the x-axis, and we're ending up with this volume. And in this case, I want to get rid of that completely, that washer, so you can see the figure a little bit better. And if I go back to reset, again, we started with just this region, and that region went around the x-axis. Again, the washers first, we had like n of them, like we had 12, and in the limiting case, as n goes to infinity, we end up with a perfect solid in that region. Again, I'm going to give you the link, so in case you want to go back and play with it, you can make some really interesting figures. But just one more time, so let's say we want to show n washers. We had 16. The maximum, I think, is 30, so let's go to 30, as many as we can. And then we want to revolve the represented rectangle. Right now, represented rectangle is there, but we could have picked represented rectangle to be anywhere we want. That's just one rectangle rotated, right? Then we're going to rotate all the rectangles to get all those washers. Right now we have 30, but to get good approximation, you want infinitely many, right? And let's just hide the washers and make it transparent to see the actual picture once again. That's pretty cool. And I was actually communicating with this person. I think he teaches at Monroe Community College, and I said, can we enter any function that we want? Because this is the only function he has entered there. Because as we do our examples, he said he's working on it. So maybe sometime during the course of the semester, the site might be updated where you can enter any function that you're working with in an example, so you can visualize what the final picture looks like. Okay, we're going to do an example in just a moment, but there's one more thing I want to mention to you, which is volumes of solids with known cross-sections. In other words, this is a more general approach. Right now, what we looked at is volume with circular cross-sections. We're always rotating it with a circular motion. But a more general formula for volume can be given like this. Volume can be written as the cross-section, the area basically, times delta x, depending on whether you're going, cross-sections are taking perpendicular to the x or the y-axis. And to explain what we mean by this, I want you to look at this pyramid example. And this is, by the way, an example from your textbook. If we have time later on, we may come back and talk about this, probably next class, because we probably won't have time today. So look at this pyramid. It's been sliced up, in a sense, as a bunch of square-shaped slabs, right? Think of it like slices. This is just one of the slices that you're seeing here, right? If you know the area of that slice, and what is the thickness of that slice in this case, but this is the y-axis, so the thickness of the slice is delta y, right? So what is the volume of that one slab? The volume of one slab would be whatever its area is, times its thickness, right, delta y. But consider this pyramid consisting of, let's say, 10 slabs, and each slab is like a square. You have the base. On top of that, you have a smaller one. On top of that, you have a smaller one, all the way to the top where you have a very small slab. So if you were to add the volumes of those slabs, basically you would have the total volume of this pyramid. And the way you can write it as an integral is the volume of this pyramid would be integral of a of y, if there's a pattern for the area of each of those slabs, and the thickness of each one was dy, And the limits of integration would be from the y-axis, like from 0 to whatever the height of the pyramid is in this case. And I also want you to check something about the units here, okay? What are usually the units for area? Square units, right? Whatever what is inches square or square feet. So let's say that it's square inches. What are the units for dy or delta y? That's the unit of length, right? What would be the, in terms of the same quantity in inches? So basically, you can also check your units when you do an integral problem that, together it's inches square, and when you're summing it all up, you're finding this infinite summation, which gives you the volume of the pyramid, where you have, basically, it's going to be cubic inches, because you're summing a whole bunch of volumes that each one is a cubic inch, basically. So again, this is a more general formula that when you have integral of a of x dx or integral of a of y dy, depending on how you slice up your region, again, that would be an equation that can be used. But today we're mainly concentrating on circular cross sections. So the two formulas that we're going to be using are, let's just review those two formulas. As a matter of fact, just one formula is sufficient in my opinion. This one here summarizes both formulas we've learned. If the inner hole is there's no hole in the region, then this inner r of x will be 0. Otherwise, you have r squared minus little r squared. Okay, now let's do some examples using this formula. Okay, let's begin with a simple one. So here's our question. Find the volume of the surface generated when the given region, which is bounded by x cubed, y equals 0, and x equals to 2, when that region is rotated around the x-axis. By the way, I was going to give you that link in case you're interested to check it later on. Let me give you that link real quick. Where was that link, I wonder? On the bottom of this page, I think. So web.monroe, which monroecc.edu/calc-nsf, in case anybody's interested. And again, you're going to find a lot more resources there for your Calc 3 class, because his main grant from NSF was for developing visualizations for Calculus 3. So make a note of that site, and I think you're going to like to visit it during your Calc 3 classes. Everybody get that? Okay. Okay, for every question that we have in this chapter, let's begin with a clear graph. Clearly, let's pick our representative rectangle. Very, very important. But sometimes for the same question, I will say, rotate it around the x-axis, then rotate it around the y-axis. For such questions, I want you to do two separate graphs with two separate representative rectangles. So we have y equals x cubed. Y equals 0, which is the x-axis, right? And x equals to 2. So it looks like I don't even need that first portion of that curve. So this is the region that we have, and it's going to be rotated around the x-axis. So I will also ask you to put a little arrow where your rotation is. So if it's around the x-axis, I want you to put this. It's mainly because I see so many examples where students, they did it the wrong problem. The question was asking around the x-axis, they rotated around the y-axis, etc. So just asking you to do these simple things, I hope that you're going to eliminate some simple errors. Okay, so we're going around the x-axis. For the disk washer method, our rectangle should always be selected perpendicular to the axis of rotation. So pick a rectangle that is perpendicular to the axis of rotation. Okay, so basically whatever this function is, that's your r of x, right? And the volume formula was volume equals, there is no hole in this region, pi times the integral of r of x squared dx. Now how do I know it's going to be dx? Because the thickness of the rectangle is delta x, right? So I know that I'm going to be using the formula with the x version of the formula. And the limits of integration will come from the x-axis, in this case 0 to 2. So what should I be writing for my r of x? X to the third, right? Because this function here was given by f of x equals x to the third. So this height, this length of your rectangle, it depends on where you are, where you're bordering the function, but no matter where you are, it's given by the function, basically. So r of x in this case is just the x cubed function. But don't forget to square it as per the formula requires. So that's how we set it up. No hole in the region, nothing to subtract, right? So it will be pi times the integral of, how do I simplify this? Power of a power, right? We multiply the powers. Now let's integrate it. And let's plug in the numbers to see what we're getting. What'd you get? 128 pi over 7 to the 7. Okay, usually we're not going to put units, but whatever the units of the given problem were, let's say that the x distances, let's say, were in terms of inches, or if they were marked in terms of feet, whatever the units are, then the final answer would be cubic units of the same unit. So if you use feet to graph your function, the final answer would be cubic feet in terms for the volume, etc. Okay, let's do another example. Okay, this time y equals the square root of x equals to 2, and y equals 0. First around the x-axis and then around the y-axis. Okay, I want to give you a minute to set this one up. So we have y equals root x is equal to 2, and y equals to 0, which is again the x-axis. So we're going to take this region and part A, rotate it around the x-axis. Okay, so once again, let's pick a representative rectangle. Since we're going around the x-axis, it will be perpendicular to the x-axis with thickness delta x. Volume equals pi times the integral of the radius. The capital R in this case is again given by the function. In this case, the square root of x function, right? Dx. And the limits are going to come from the x-axis from 0 to 2. So here we have pi times the integral of x dx and looks like we're getting 2 pi. Now part B is going to be a bit more challenging. Let's take a look at part B as well. By the way, after you draw the two-dimensional graph, it wouldn't hurt to also do a three-dimensional graph if you choose to. But I suggest you don't put it on the same graph because sometimes it complicates the matters worse. So So this was the original function, and the rotation was around the x-axis, right? Just to give an idea, what kind of a volume have we created here? If you go around the x-axis, roughly speaking, this is the kind of graph that we created, and this is the solid that we found the volume for, right? So we went around the x-axis, that is a solid generated. Okay, now we're going to take the same region, but go around the y-axis. Let's see. Remember what my suggestion was? Create a separate graph for this. Don't try to overcrowd your graph, then it's very easy to make a mistake. So let's go ahead and create another graph. The same region to begin with, right? Root x, x equals to 2. But this time the rotation is around the y-axis. So as a three-dimensional graph, what would that look like? We're going around the y-axis. Exactly, there's going to be a hole in the inside. We're going around the y. So very roughly speaking, you know, just to show you, it's a completely different picture than the one we got in part A. This one has a hole in the middle, right? The outside part is like a cylinder, and inside, how would you describe maybe the shape of the hole? It almost looks like a cone, except that it's not straight edges, it's like a curved edges. So that part has been taken out of the solid, okay? So we're going to try to find out the volume of this figure. Okay, what kind of a rectangle should I be selecting for this example? Since we're going on the y-axis, remember, you want to always select a perpendicular rectangle to the axis of rotation, because that's what's going to create that perpendicular rectangle when going around the axis of rotation. That's going to create a disk or a washer. So like here you would have one washer created. If you pick this one and you went around your axis of rotation, you would have one washer right there, roughly speaking. And then we want to add those up to build our total volume. What is the thickness of this rectangle? The thickness is delta y, right? In the integral, we use it as dy. Okay, there is clearly a hole in the region, so we're going to use the more general formula, right? The more general formula was volume equals pi times big R squared minus little r squared, dx or dy, depending on the problem. For this problem, which one will be used? Dy, based on the selection of our rectangle. We have to use a dy. Okay. So let's now set it up based on the given problem. Pi times, okay. Big R is your outer radius, which is distance from here to here. What is that distance, no matter where you are in the region? What is that distance? That's a constant of 2 units, right? So big R is equal to 2. So in this integral, we're going to have 2 squared. Okay, now let's worry about the little r. Little r is the inner radius, which is this distance from here to here. That's the radius of the hole of the washer. That's our little r. Okay, what will that be for this question? That's a little bit tricky to obtain. And whatever it is, we have to square it as well. Let me just put a reminder there. Okay, basically, distance to the y-axis is always referred to as x. So basically, that distance, that little r, is the bigger distance, which is 2 units, minus x. But for this question, okay, actually, for this question, again, once again, what is the distance from the y-axis to this point right here? From here to here. Again, normally that distance is given by x, but for this question, what is our x? We cannot write it in terms of x. What is the reason? Because earlier we decided this problem was going to be set up in terms of the y variable, right? So normally the distance to the y-axis is given by x. But for this question, what will it be? Exactly, because x is equal to y squared since the given function was y equals root x. If you solve for x there, x is equal to y squared. So I need to put here y squared. But why do I have that outer squaring once again? Because the formula said big R squared minus little r squared. If you like, you can write an intermediate step here. You can say big R is equal to 2 units and little r is equal to y squared units. Then you go back and you put it into your formula. How about the limits of integration? Where should it come from? From the x-axis or the y-axis? How do I know which axis it should come from? Did you use delta x or did you use delta y? Delta y. That means your variables must be in terms of y, and your limits of integration must come from the y-axis. So what point do you think corresponds to right here? If this is 2, and this is a function, the square root of x function, what do you think will be the y limit up there? Root 2, right? The square root of 2? Because it's a function y equals root x, at x equals to 2, you have y equals root 2. So the limits are going to be from 0 to the square root of 2. Let's simplify this a little bit.
R equals to y squared.
Because the inner radius is technically should be just x units, the distance to the y-axis is given by x. Like in a little bit, we're going to do other problems, and distance to the y-axis is given, difference to the x-axis is given by y, and difference to the x-axis, okay. Difference to the y-axis is always given by x, and difference to the x-axis is always given by y. So normally you would want to put there x squared, but you cannot have x because everything has to be written in terms of the y variable. So here we have 4 minus y to the 4th. And let's integrate it. Which I'm sure you can simplify this, but I don't want to worry too much about the arithmetic part today. I want to be able to give you lots of examples where you can see lots of setting up of the problems, because that's what's really important for these questions. As you can see, when you integrate them, the integrals, there's never going to be like a trig substitution or partial fractions or anything like that. So I want to do plenty of examples where you can see different kinds of setups. Okay, let's do another example.
So we'll show by that. R being equal to y squared.
So for this question also, I want to give you plenty of time, so I'm going to pause the recording, give you a little bit of time to set up, and then we're going to come back and discuss it.